In this video, we will see about the speed control techniques of induction motor. So there are different techniques. In this video, we will see about stator voltage control and stator frequency control and the main torque equation, speed torque characteristics, and what are the advantage and disadvantage of each method. Then we will also solve a numerical problem to understand the concept. There are different speed control techniques for induction motor, that is by varying the stator voltage, that is stator voltage control, varying the frequency of the stator, that is stator frequency control, varying both the voltage and frequency, and stator current control, static rotor resistance control, and slip power recovery scheme. So out of these, the first four can be used for both squirrel cage and slip ring induction motor, whereas the last two techniques can be implemented only in slip ring induction motor. So in this video, we will be seeing only about stator voltage control and stator frequency control. First we will see about stator voltage control. So the torque equation in three-phase induction motor is given by T is equal to this equation, which we have already derived in the previous video about induction motor drives. So in that you will get this relation. So we can write it as torque is directly proportional to voltage square. So by varying the voltage, you are able to vary the torque. So the motor torque is directly proportional to the square of the supply voltage. How to vary the stator voltage? Conventionally, what is done is they will use auto transformer. So if you use an auto transformer, you are able to control the voltage applied to the stator. Or you can use some resistors in each phase. You can connect the resistors in series with the stator winding. Thereby you can control the voltage applied to the stator. But in power electronics, we can use three-phase AC voltage controller because we want to vary only the voltage. So AC voltage controller is sufficient. If you want to vary the frequency also, you can go for cycloconverter. But here we were using only voltage. So for that, AC voltage controller is sufficient. So here by varying the firing angle of the thyristor, the RMS value of the stator voltage is controlled. So the motor torque, which is directly proportional to the square of the voltage, will be controlled, and thereby you can control the speed of the induction motor. Let us see the speed torque characteristics. So it is drawn for different voltage. V1 represents the rated voltage and V2 and V3 are reduced voltage, and TL represents the load torque line, which in this case a fan load is taken, so the line is like this. Now this intersection point will give you the speed at which the motor will run for a particular voltage. So in case of V1, the speed is going to be N1, and in case of voltage V3, the speed is going to be N3. In all the three cases, you can see the maximum torque occurs at the same point. Though the magnitude of the maximum torque is different, the slip at which maximum torque occurs remains the same. And the important point to note here is that though we are able to reduce the voltage, here the speed range is very less. For each voltage, the speed differences is very less. It means that your speed control will be very narrow. So the limitations of this method are the range of speed control is limited, and whenever you use power electronic converters, harmonics will be introduced into the supply and the load, and the input power factor will be low, and this method is suitable only for speed control below rated speed, because you cannot increase the voltage above rated voltage, only you can reduce the voltage level. So it is suitable only for speed control below rated speed. So this is used in many applications, especially for starting large motors, and it is suitable for low power drives like fan, blowers, centrifugal pumps. In stator frequency control, the frequency of the stator is varied to control the speed of the induction motor. What is the frequency of stator? That is the supply frequency. We know the speed of the induction motor will be always close to the synchronous speed. Synchronous speed is given by 120 F by P, where F is the supply frequency and P is the number of poles. So if I change this supply frequency, the synchronous speed will change. If synchronous speed changes, the motor speed will also change. The voltage induced in the stator winding is given by this formula. V is equal to 4.44 F pi N into K. So these two are constants. If you see here, V is directly proportional to frequency and flux. Suppose this voltage is kept constant and I am changing the frequency, then the flux will change. If flux changes, torque will change. Okay. So based on this concept, this stator frequency control works. Okay. V is kept constant, only we are changing the frequency. From this synchronous speed equation, we can see that if I reduce the frequency, speed will reduce, and if I increase the frequency, speed will increase. So there are two conditions. Either you can increase the frequency or decrease the frequency. So let us check one by one. First I am reducing the supply frequency. So take this equation. Here the voltage is kept constant. I am decreasing only the supply frequency. If I reduce frequency, the flux should increase so that the voltage remains constant. So the flux will increase. If flux increases, torque will increase. It is a good thing. But what happens? The magnetic circuit will get saturated and it draws more saturation current. It leads to more core losses, and at low frequency reactance will be less because it is a function of frequency. So the impedance will be less and it draws more current and more losses will be there. Because of that you have low efficiency. So this method is not used. Next we will increase the frequency and check. Now at constant voltage you are increasing the frequency, so the flux will decrease. So if you increase the frequency, the synchronous speed will increase, motor speed also will increase, but this flux is directly proportional to the torque. So the torque will decrease and both maximum torque and starting torque will decrease. How to achieve this stator frequency control? That is how to change the frequency of the stator winding. By you can see here an inverter is used to supply the induction motor. So if you change the output frequency of this inverter, you can control the stator frequency. So the inverter needs DC supply. It comes from a diode bridge rectifier which is fed from a 3-phase AC supply. Let us derive the maximum torque equation. We know the torque at rated supply frequency FB is given by B represents the base frequency or this rated supply frequency. So it is the torque equation. Now we are changing the supply frequency to a new value F. Let us take one ratio K is equal to F by FB. Or if it is in radians per second, you can write omega s divided by omega b. So in this equation you have to change the new frequency. So omega s is what? K times omega b, and when you change the frequency, reactance will also change. So you change the reactance also. Here as a frequency we have increased the frequency, this reactance part will be more when compared to the resistive part. So the stator resistance can be neglected. So you are getting this torque equation. So for this torque, let us find the slip at which maximum torque occurs. So how to do that? You differentiate this with respect to slip and equate to 0. You will get the condition for maximum torque. So Sm is equal to R2 divided by K into x1 plus x2. This is the slip at which maximum torque occurs. Now you have to substitute this in the torque equation to get the maximum torque. Substitute this slip value in the torque equation and get the maximum torque equation. You simplify this, you will get the maximum torque equation. So the maximum torque at base frequency you can find by K equal to, substitute K equal to 1, that will be the maximum torque at base frequency. So we are finding this because we want the ratio of these two 1. The maximum torque at base frequency is given by this one, and maximum torque at new frequency is this one. Let us divide these two so that we will get a relation between the maximum torque at base frequency and maximum torque at new frequency. So Tm into K square will give you Tmb. Tmb is a constant. Let us see how the maximum torque get reduced. So we have this relation, and suppose if the rated frequency is 50 Hertz and the torque at that frequency, maximum torque at that rated frequency is 100 Newton meter. Let us increase the frequency to 100 Hertz. So in such case, K will be F divided by, that is new frequency divided by base frequency. So K is 2. So if you substitute K equal to 2 here, you will get new maximum torque as 25 Newton meter. That is, if I change the frequency from 50 to 100, my maximum torque is getting reduced from 100 to 25 Newton meter. So this method is also not very efficient method, because as you increase the frequency, your maximum torque is getting reduced. You see the speed torque characteristics. So here it is drawn for torque and K. Okay, K is nothing but new frequency divided by rated frequency. So when it is equal to 1, that is the normal characteristics you will get. But if you increase the frequency, keep on increasing the frequency, your maximum torque level is getting decreased. So above rated frequency, Tm is getting decreased. So in this stator frequency control, the machine induction motor behaves like a DC series motor, and it here it operates in flux weakening mode. So the air gap flux is reduced because we are increasing the frequency, flux is reduced, so torque is reduced. Let us do a numerical problem. A 3-phase squirrel cage induction motor drives a fan load. No load rotational losses are negligible. Prove that the rotor current is maximum when the slip is 1 by 3. And second part is find the expression for maximum rotor current, and if the motor speed is 1350 rpm and synchronous speed is 1500 rpm, determine the maximum current in terms of its rated current. So there are 3 subdivisions. Let us go one by one. So the first one is that we should prove that the rotor current is maximum when the slip is 1 by 3. And fan load is given and the rotational losses are negligible. Let us take the first part alone. So what is given? It is a fan load. So for fan load, the load torque equation is given by K omega m square. Next one, no load rotational losses are negligible. It means that your output power is equal to load power, or that is also equal to mechanical power. Actually, in mechanical power, if you subtract the rotational losses, you will get the output power. Since here rotational losses are 0, the mechanical power and output power are same. So that is equal to load power. So the load torque is given by TL equal to K omega m square. So power will be torque into omega. So torque into omega will give you the load power. So that is equal to PL is equal to K omega m Q. So we can write PL is equal to K omega m Q. What is PM? Mechanical power is equal to 1 by S, 1 minus S into Pg, where Pg is the air gap power. So 1 minus Pg is equal to, I can equate this to K omega mq. So equate these two. You know what is Pg? Air gap power is equal to 3I2 square into R2 by S. So substitute it, find what is I2. So if you simplify this, you are getting the equation for I2. What we have to find is, you have to find what is the value of slip when this I2 is maximum. This is the I2 equation. Let us differentiate this with respect to S and equate to 0. So we can find the slip at which this rotor current becomes maximum. Now, how to differentiate this one with respect to S? You have a constant term. This which is inside the square root is a constant term, and here you have two terms in terms of S. So this is like U into V, differentiation of UV. So differentiation of UV is U dash V plus V dash into U. So you can apply this rule and find what is the value of S. So this is constant into U dash. So square root of S, if you differentiate, it is actually S power half. So if you differentiate, it will get half into S power minus half. So it becomes 1 by 2 root S into V, this term, plus V in V dash. So if you differentiate this one, you will get 0 minus 1. So 0 minus 1 into U. U is root S. That you equate to 0. So you simplify this one, you will get S is equal to 1 by 3. So the first part we have completed. So we have found that the rotor current is maximum when the slip is equal to 1 by 3. So first part of the question is solved. Next part, we have to find the expression for maximum rotor current. So rotor current we know. We also know the slip at which the rotor current becomes maximum, S equal to 1 by 3. So you apply S equal to 1 by 3 in this equation, that will give you the maximum current expression. So if you substitute S equal to 1 by 3, you will get I2 max. Next question, we have to find the maximum current in terms of its rated current. So motor speed is given and synchronous speed is given. So let us find what is the slip value. So slip is coming around 0.1. Now already we have calculated what is the maximum current, we know. We have to find what is the rated current. So for rated current, you substitute slip is equal to 0.1. So instead of S, you substitute S equal to 0.1, you will get the expression. Now you divide these two, you will get the relation for maximum current and rated current. So I2 max is equal to 1.35 times I2 is the relation. The points to remember here are the speed of the induction motor can be controlled by stator voltage control, where the torque will be directly proportional to the voltage square. So, but in this method the range of speed control is very limited and it is suitable only for speed control below rated speed. And AC voltage controller can be used to vary the stator voltage. In stator frequency control, ns is equal to synchronous speed is equal to 120 f by p. So, by varying the frequency, you can vary the speed of the induction motor. At constant voltage, if the frequency decreases, the flux will increase, but this leads to magnetic saturation. But if we increase the frequency, the flux will decrease, and if flux decreases, the torque will decrease. So, three-phase inverter can be used to vary the stator frequency. If you like the material, please subscribe to Read Electric Vehicle channel. Thank you.